delighted to be here in Port of Spain. Right, so what I thought I'd do with you this evening is to give you a little snapshot of some of the technical aspects of some deep water sedimentology and deep water exploration related sedimentology. I'd like to focus on one particular type of reservoir element, but to do that, I think the best way to start off is to take you back through maybe your current understanding of what these frontal splays actually are, or what they look like on the seafloor, sometimes called lobes. So the title of the talk, if you see my abstract, is characterization of what is quite an elusive and undersampled element in modern deep water settings. So I'm going to show you a range of data styles, from side scan sonar and drop cores and things from modern research cruises, through to seismic data and its application, and analogy with seismic, and outcrop examples too. So it's a range of different styles of data to try and help us understand better what these things actually are. If you want to follow a very exciting Twitter feed, Deep Marine, for what I tend to put on this is lots of links to exciting papers and the things that most of us don't have the chance to read through all the time, if you're interested. So let's start off with a little outline on what I'd like to show you. First of all, just some basic ground rules on this. What do lobes and splays actually look like? Most of us think back to, if you haven't been working on turbidites, thinking back to turbidite lobes or submarine fans and all these things as big radial shaped features which we've been mapping and interpreting for some time. So within the context of lobes, I want to review some of what we understand about sheet systems in general, because lobes and splays are different types of deep water depocenter, so they should have a sheet type morphology, or should they? So I'll go through the architecture and geometry and style. I'll go through with you a review of where they occur on slope, margin and basin profiles, and I'll help you to look at the different ways we recognize these things. There are many different terms, if you look at the second last bullet point here, that people use in different companies, in different research groups, in different age groups maybe, I don't know. Lobes, frontal splays, superfan lobes, channelized lobes, distributary lobes. Some of these terms are really quite awful. Mouth splays. Which one of these, what are they? Are they all different? Are they the same? It's one of the few styles of deep water sand body or architectural elements, things that we recognize as building blocks of reservoir systems, for which we don't really have a proper series of descriptors. We haven't really got that. We don't have, for example, different hierarchies like we have for channels, channel elements, channel complexes, channel sets, etc. We don't have that. So really it's an open book. It's something that's been a bee in my bonnet for a long time now. I'll also bring in some sequence stratigraphic aspects. So let's start off with our first reminder of what splays and lobes are. So I went down the high street in Aberdeen and went to Blackwell's bookstore, and I picked up a geology textbook for secondary school, high school students, to see what they're telling our children about turbidites. And there was a whole page on turbidites. And in that page they had a model that looked like this, which showed a deep water slope area, a continental slope with a shelf break here, the shelf area up here, the lower slope, and then this classic radial fan with what looked like some sort of distributary network of channels. The classic model from the 1970s, which looks a little bit like a delta or alluvial fan, maybe, things spreading out over the surface. Is that what we see in deep water? This was from the textbook I've just mentioned, the school book, and it shows a nice colored block diagram. It shows a shoreline area with some deltas. It shows a shelf area with purple arrows showing you the direction of movement of littoral drift cells and longshore drift of sand on a shelf, which is fantastic. Sometimes moving sand from a delta along the shore and maybe being captured in some sort of submarine canyon, which is incised on the shelf break back onto the shelf area. So turbidity currents, subaqueous, sediment-laden gravity currents of different types will be moving downslope by gravity, flushing through here during storms or earthquakes or river floods and different types of triggers, and depositing on the basin floor. Or if not, on the interslope if you've got topographic confinements. And what I loved about this particular school book was that it seemed to have a different type of shape on the edge of what looked like radial yellow-coloured submarine fans, deep-water fans. And those were these orange things. And I thought, where on earth did these orange things come from? Because those are the types of things that we see on the sea floor. And that really is the content of most of the presentation I'm going to give you. Most lobes, most distal accumulations of sand on a deep water setting are actually skinny little bodies, little fan-shaped bodies, and they're often dislocated from each other like this. And that's the basic premise of most of what I'm going to show you. If you take back, look back at the block diagrams from the early 1990s, from Harold Redding and the BP models and Marcus Richards, you see other types of models which show similar types of shapes, but which we don't use very often. Almost like a bird's foot delta, like the Blaze delta lobe in the Mississippi Delta. So how much of these things are real? How many examples of them have we really ever seen on the seafloor? And how much can industry seismic data help us to embellish our understanding, improve our understanding of these features? Let's go back to the early discoveries of these features on the seafloor, and they were mostly described from places like the California borderlands. And this work here was done by Dan Piper, looking at the Navy fan here, just off a very narrow concertinaed shelf margin. And they knew there were deep water canyons or slope channel complexes feeding out onto some sort of bump on the seafloor, which they call a submarine fan. And yet sitting on top of it, rather than just having a radial conical shaped fan with ever decreasing size channels, they recognized more elevated linear channels with lobes on them, and at the end of them a little blob. And they call these superfan lobes, and then we more or less forgot about them for 25 years. These are the more common types of geometry of the sandy bodies that we see in deep water. So let's start off with a cartoon that I threw together of every single lobe or frontal splay, any of those terms I used on the first slide. How many of these things have any of you actually seen? I've seen all of them. There are no red herrings in this lot. And rather than having a lobe, like a delta lobe or a distributary mouth bar or something like that, which we're used to seeing on the shells in sandstone and clastic areas, we often have things that look like a paddleboard or a toilet brush, or I don't know, some sort of paired seeds on a tree, or well, you can imagine what we call this one, or trumpet-shaped features, or gaggles of little blobs of sand. And all of these are real shapes, and they're all the real geometries of depositional bodies at the deepest and most distal parts of turbidite systems. And yet we don't seem to have any clear model or understanding of what they are. When you think of sheet sands or turbidity current deposits in general, gravity flows spreading out on the sea floor, you tend to think in terms of laterally persistent, continuous, rhythmically deposited layers of sand. Do we have continuous sands in the sea? Yes, of course we do. We've got very laterally persistent sands. I'll give you an example of how extreme laterally persistent sands can be. This is from the northwest coast of Africa, so we're up the border between Morocco and Western Sahara, or southern Morocco, whichever way you're leading. These are the Canary volcanic islands here, the Madeira volcanic island to the north, and the grey areas are abyssal plains. The middle one is called the Agadir Abyssal Plain, and it ranges in depth from about 3,500 to 4,500 meters water depth. And if you go up dip, and I hope you can see this from where you're sitting, where the red line is the transect coming down the whole basin slope, the red line goes from the head of the Agadir Canyon here to the very start of the basin. That's 250 kilometers of canyon before you get out onto the basin floor. And this transect here shows you the different gravity cores that have been taken from the sea floor here. The three middle ones, you can see green colors and purple colors, are individual turbidites. So sometimes, yes, we can have layered turbidites which can go for many hundreds of kilometers. And we spent 5 weeks on the Charles Darwin, I was co-chief scientist in 2004 here, coring along this deep water basin floor, hundreds of kilometers from the shoreline, the shelf break, and we have beds which are very laterally persistent. So yes, we do have layered sands which are very laterally persistent for hundreds of kilometers sometimes, but generally these are the background layers to blobs of sand, the lobes that I'm talking about. Here's an outcrop photograph from Ireland, where I'm from the west coast of Ireland. These are from Upper Carboniferous. These are Lemurian-aged intercontinental basin, but it's a marine basin, maybe an epicontinental basin. And the types of architecture that we see, architecture, just the general building shapes and continuity and geometry, that's what I mean by architecture, rather than artistic style. And the upper part of the cliff here, which is 45 meters high, has got very high net gross, high percentage sand, amalgamated sand bodies. So these thick sandstone bodies range in thickness between maybe, say, 2 and 6 meters. And if you look inside them, you can just about see weathering out these little interleaves here, which are amalgamated surfaces. So a turbidite sandstone was deposited, and then another flow came along and maybe welded onto the previous one by eroding away the top of the previous bed. So we have high energy flows which stick to each other and give us this classic sheet type architecture. So we look at the lateral continuity. The beds seem to be, on a scale of 100 meters or so anyway, along these cliffs, fairly rather laterally persistent. But there is some scouring. Feast your eyes on the upper part of the cliff and you can see evidence of little smiles, little pinching out of some of the beds, scouring in some of the units. And you're trying to understand what were these features. What would the sea floor look like if you looked on top of these things? And how laterally persistent really is that block of multiply stacked amalgamated sheet sands? Not very far, actually. Not very wide, not very long. I always trip over everything within 2 meters. The lower part of the cliff has got more layered turbidite sandstones, which are much more laterally persistent. So the splays, the frontal splays, etc., are this type of body, and I want to try and tease out some of the shapes. Let's take you over to the distal part of one relatively fine-grained system in the Gulf of Mexico, the Mississippi fan, of course. And back in the 1980s, the British Institute of Oceanographic Sciences, as it was then, surveyed all of the US economic zone with medium-range side-scan sonar, the Gloria tool, which operates at a frequency of 6 Hertz, giving an acoustic backscatter image of the sea floor, which penetrates a little bit, 10 meters, 20 meters. So the grey tones you see here are the deep water basin floor. The blue line is the shelf break to the west of Florida here. And the cartoon on the bottom right-hand side shows what happens when you go from the Mississippi Canyon, which is 25 kilometers wide or so, depending where you are, down the slope in a very much a deep channelized system, and way down at the end of the system we have these levade channels which dump sand out onto these lobe-shaped bodies. So for some time our understanding of the distal Mississippi was that we had these lobe bodies. The scale here on the black stick is 100 kilometers. So you're talking about very large bodies, very radial shaped bodies that were mapped at a very loose and small scale. However, the side-scan sonar right at the edge, right at the base of the Florida escarpment shows a different story. So what you're expected to see, remember, are layers of turbidites that spread out and lose energy and form very thin layered fringes on the edge of the system. Whereas in fact this is what they discovered back then. At the edge of the system, in fact, you have a levade channel coming down where my arm is, through the 112 degrees north here, and then it opens out into linear tongue-shaped bodies, right as far as you can go on the Mississippi deepwater fan. So the turbidity currents are starting off way up here in the canyon in recent times as slumps from the sides of the canyon that are being flushed into perhaps by storms or other types of activity. And they start off as very muddy flows with a small amount of sand, and they come all the way down the canyon, down through this channel complex, and as they come down as a turbulent flow, all turbidity currents are stratified, so the coarser grains tend to be lower down in the flow, and the silt of the clay is higher up. So as it comes down, it spills over the levee, spills over the levee, So as the flow comes right down to the end of the system, it's losing clay and losing silt. So the bottom of the channel has got a slug of sand, effectively losing clay. So by the time it gets to the bottom, it's out of energy and it goes on the edge of the system as a sandy feature. And these have a sort of a Christmas tree type shape to them. The edges of them are very serrated. The scale on these features, they're about 3 kilometers wide or so, and they can be many kilometers long, 10 kilometers long maybe. And if you drop a core anywhere around the feature in the black low backscatter area, there's no sand at all. There's maybe some very thin silts, but it's mostly marl and deep water clay. So whatever's happening here, these flows are stopping very quickly, like a watery slurry, a Korean toothpaste, or a washy wet concrete, or a low viscosity type of mud flow. But they're sandy, and we know that. An analogue might be a pyroclastic flow. So here's a flow deposit from a pyroclastic flow from Mount St. Helens. Most of you probably won't remember that eruption. And the pyroclastic flows were particularly violent, but this one deposit is about 1 kilometer across, and it's mostly made up of pumice and ash and things like that, of course. But the thing about it is the similarity in shape with what I just showed you from the end of the Mississippi. We still have these little features coming out at about 45 degrees by lofting of the flow and by gas escape. And the pyroclastic flow, remember, has a lot of dynamics, subairity, similar to many aspects of submarine density currents, like gravity currents. So it's stopping very suddenly and freezing at the end of the system. Isn't that tantalizingly similar, really? You look at the shapes, there are very few shapes in nature that don't have that type of expression. So the mechanism, the rheology of the flows, means that the turbidity currents, like mud flows, like pyroclastic flows at the base, are moving as a laminar flow and freezing very, very suddenly. There's a cartoon which I put together which shows the real type of, these would be the toilet brushes, I suppose, long, extensive features at the end of the system. And if you drop cores anywhere in here, there's no sand at all. They're separated from each other. From a reservoir perspective, if you think about the quality of the reservoir, these particular types of lobe bodies or frontal splays, the sediment is being recycled from the Mississippi River, 15% only of which is sandy, the material coming in to the Gulf of Mexico. It's being knocked around on the shelf for a while by littoral drift cells, by longshore drift, and eventually it gets out into the deep sea. So by the time these are modern piston and gravity cores from those features, by the time it gets right out to the end, 700 kilometers away, the grain size range is very narrow. So 90% of any sandstone bed in any of these frontal splays is within 2 adjacent Wentworth grain size classes, which would send me to sleep when I was a student, but now it makes a lot of sense because very fine grained sand, if you think back to the definition of very well sorted, that's exactly what it is. So these are extremely well sorted to very well sorted sandstones, fine grained, very good reservoir properties, and otherwise they have occasional clay clasts inside them which come all the way down to the end of the system. So we've got bodies. Think about if you're exploring for accumulations of sand. The last thing you would expect, normally, intuitively, would be a fine-grained system in deep water, or a fine-grained tine in a coarser-grained system, where skinny, fairly muddy channels all the way down to the end, and suddenly your reservoir potential upside is way out there somewhere, hundreds of kilometers. You get a fine-grained Orinoco slope, or a fine-grained Magdalena slope, and next thing way out there you've got blobs of sand. Well, I would say it's the rule rather than the exception, particularly when you're fed by linear levate channel complexes, because it allows the flows to propagate right out to the end of the system, and it strips them of clay. This is a shell paper from deepwater Brunei subsurface. This is a shallow subsurface analog study by the Metznier et al. Group. And there's a modern seafloor canyon cutting through the section. But all I want to show you are some of the main architectures that we see of a muddy slope. This is the northwest slope of Malaysian, Bruneian, Borneo, Kalimantan. So we're looking at the deep water slope going to the northwest, muddy, fine-grained, tectonically active, thrusts, mud walls, mud diapirs, etc., etc. And we have channels coming down the slope, which are quite muddy, except they've got a high amplitude here you can see in the shallow subsurface, which you can ascribe as a proxy to sand in the proximal parts of the levees. Skinny little things with low volume of sand overall, and just at the bottom, frontal splays. Right at the end of the system, as you decrease the gradient of the slope overall, and as you decrease the height of the levee, you get these frontal splays. So here we've got an example of one of those features here in the shallow subsurface, where we've got high amplitudes, you've got a little bit of erratic patterns on the top and diffractions, tiny little channels on the top, and that's what you see. And you're thinking, how thick are these? How extensive are these? Normally something like that, as a composite reservoir body, will be 30 to 50 meters thick. However, individually, there are lots of little blobs of frontal splay associated with it. So, let me take you to try and understand this better, to try and understand why we don't know more. There are a few reasons. I've been on a few cruises, 12, only looking at turbidites in various places, Black Sea, Mediterranean, Northeast Atlantic. This is an example of a cruise of an area I've been to twice, off the Gulf of Cadiz, outside the Straits of Gibraltar. And one of the problems we've had with things like that, you can see it, it's a lobe, it's got a channel feeding it, are very simple problems. Gravity cores, piston cores, drop cores, box cores. If you drop them down onto that thing, onto fine-grained sand on the seafloor, and try and pull up your gravity core and hope that the core catcher will hold like a colander, as you pull up the gravity core, all the sand starts washing out. I know it sounds like a stupid problem, but it's something that traditionally has a very poor recovery on the deep sea floor. If you drop a gravity core 6 meters long with a 1.5 ton weight on top of it, just hold it above it and drop it 100 meters onto the seafloor, it hits the seafloor and falls over more than often. So we have very few data sets, number one. We've actually got more subsurface analogues than we have seafloor analogues. So let's have a think about this one. Let me show you its shape, its cause, its analogy, and then show you what I think is the only image that we have, that's a bit controversial, on the seafloor of a high resolution image of the top of the frontal splay. It's not published either, of course, in someone's drawer in Moscow. So let's go to the Gulf of Cadiz. So there's the Straits of Gibraltar, there's the northern coast of Africa, Tangier. This is the southwest coast of Spain, Atlantic coast, and the southwest coast of Portugal. And the Gulf of Cadiz here, outside the Straits of Gibraltar, is the connection with the Mediterranean. So we've got a very relatively saline body of water in there. So there's an outflow, quite a strong, low, dense, saline outflow from the Mediterranean, and it comes round towards the north. And that's what the yellow arrows are here. If any of you are familiar with the coastline from Tarifa all the way across to the Algarve, which is where people go on holidays a lot in Europe, the Algarve is golfing, sandy links, it's very sandy shoreline, a very sandy shelf, longshore drift, moving sand along offshore all the time. But we also have sand on the upper slope. It's unusual. But as a consequence of sand being moved on the slope, it's a very good analogy for us, because we can think about what happens when sea level is lower in other places. So sand is moving along here, along the upper slope, and we have cores from these features, just like the ones I showed you in the Mississippi again. This is on the sea floor from 0 centimeters down, 82, 145. These are just different core barrels from the different cut barrels from the gravity core, down to 2.28 meters. So what types of structures do we see? Well, not a lot actually. We don't see any Balmer intervals, the Balmer A, B, C, D, E. We don't see laminations. We don't see ripples or cross-bedding. We don't see any primary tractional fabric at all. So we can never say that the bed was being deposited like that as the seafloor, as the flow went over the seafloor. So this is being deposited en masse, as a slurry, very, very quickly being deposited, with no grading or anything inside it. It's active now because there's sand on the seafloor. And there's shale clast inside it, just like we see in the Mississippi, the same grain size range. And just to show you, we do some work. There's a grain size sampling here every 10 centimeters. The grey is mud and silt, that goes up to medium silt, up to 0.03 of a millimeter. And above that we've got fine and very fine sand, and and a medium sand. So again, the definition of very well to extremely well sorted is met in these beds. So let's think about how they form. Well, there's that terrace, there's that interslope terrace along which the strong Mediterranean outflow is moving 20, 30, 40 centimeters per second at different times, which can move medium grain sand very easily. So you've got this whole sediment drift on the northern margin of the Gulf of Cadiz, and it builds up on this terrace. So it's not a shelf. The shelf is up here. The terrace is an interslope terrace. It's an interslope basin which is horizontal. It's parallel to the slope. And the sand builds up here on the edge. It oversteepens, and then it starts to collapse. Just like a shelf-edge delta would if you drop the sea level and push your shoreline out towards the continental shelf. Rivers would cut down as incised valleys. You'd feed out these very sandy deltas. They'd oversteepen their cliniforms and collapse. And when a sandy delta collapses, it collapses as a slump. And the slump is now at a higher angle after it's slumped than it was before. So it goes again, and again, and again, and again, any child playing on a beach. Retrogressive headwards failure. And those retrogressive headwards failures we can see here on these sandy accumulations. And they form a fire hose of sand that pumps downslope onto the lower part of the continental slope. Another interesting aside here is that this dotted line is an unusual interface in the ocean. It's a mid-ocean volume surface in the central Atlantic, where there's a much even denser brine on the bottom. So the flows are coming down the slope, and if there's any fine-grained material, it hits that density interface and lifts off into the middle of the Atlantic. Whereas the sandy stuff keeps going, the dense flow. So it's a very dense flow here, and then eventually it just goes into these sandy lobes. Close-up look. Let's start off with this headwards area where you've got these slump scars, and they're very dramatic. It's vertically exaggerated. This is hull-mounted bathymetric profile of data that we have from the Russian ship that we collected this from. So these scars here have cut backwards, like you'd see any slump scar on a mountainside that collapse backwards. But quite quickly we think these happen. And the flow comes down this way, or comes down that way, or comes down that way, down through quite a tiny little channel. And the channel we've imaged quite nicely on side scan. This is a deep tow side scan sonar. So you tow it about 90 meters above the seafloor, and you can steer it and keep it at that depth. And it goes at about 1 knot per hour, and it's got a very narrow swath width. So we're looking at a 100 kilohertz frequency side scan sonar data set. This is acoustic backscatter from the seafloor. If it's sandy, usually, or bedrock, the acoustic image bounces back to the fish, so you get a hard response. If it's shady or in shadow, it gets absorbed by the seafloor. So it's not an optical image at all, but it's a very high resolution image of a channel. And the channel, you can see, has got terraces. It's been cut down, it's been deflated. It's only about 100 meters wide. It's only about 15 meters deep. So it's small, it's a tiny little thing. And as you go upwards, you can see that we have these. This is the ship's track, by the way, of the mosaic. You're looking at a planform image of the seafloor, going down slope to the left. The arcuate shape you see here is like a little waterfall. And these are very common in deep water. They're nick points that cut backwards. The turbidity current, like a waterfall, will do the same thing here. Now, 100 kilohertz is very high frequency. So if you're driving your car around with the music on loud, everyone hears the and not right? So high frequency data are only going to be recorded here by very shallow penetration. So all you're seeing is maybe 20 centimeters to a meter below the seafloor. And if you look to the lower part of the image, you can just about see the ghosting of previous channels here. So in fact, this is not a large fairway of big channels. It's a whole lot of small, little channels, tiny channels. And when they're dead, they switch and they fill with clay, which means that the lobes we're studying, you never see the feeder. And on seismic, when you're looking at attribute maps and you're trying to work out where your sand bodies come from, you'll probably never see the feeder. It's just too small, it's filled with mud, it doesn't image on the seismic. So don't look for them, that's what I would say. And the next image is just below this to the west is the only image, I think, as I promised you, of one of these lobes. Well, it is not the only image because it was on the poster of the GSTT that advertised the talk, but apart from that, this is the edge of the feature here. This is what should be a fining and thinning lobe here, and it's covered with tiny little channels. Channels which are maybe 10 meters across, less than this room and not as high as me. And that's what characterizes the whole top of these sandy, slurry types of distal frontal splays. If you drop a core, as we've done anywhere here, if you get a retrieval of sediment, it will always be massive, well-sorted, structureless sand. There will never be any layers of clay. All of the features you see here are patterns on top of the sand. If you drop a gravity core here or a piston core here, you just get clay with very, very thin silts or marls. So it's a very dramatic departure from our understanding of these bodies, and this is just me drawing cartoons. So that's what it looks like on the sea floor, this analogue that we use as an analogue for what happens when sand is pumping onto the sea floor from the shelf, usually during lowering and some parts of lowered sea level. Usually during the falling, in fact, is where we get this, even though it's forming an interslope area. And these multiple channels are all active at different times, and the epicenter is shown here as this elongate frontal splay. That's how a turbidite lobe forms. Multiple compensating bodies, all covered in tiny little skinny channels on top of them, all being fed at different times. The cross-section here is just an interpretation of what we've been coring, but there is some lateral shifting of them because the accommodation space, the space available to dump something is shifting sideways, and that's just an interpretation. You could look at, think of the big questions: how thick are they, how big are they, what's the reservoir potential of these things, where are they distributed? This is a 7.5 kilohertz seismic profile which goes with the side scan sonar, so it's all mounted, it's in the fish. And this is a very dramatic image. There's the side scan sonar here, there's one of those little channels that we saw in the previous image, and again you can just see the thin lip either side of a very narrow channel. And there's the same feature down here. That is a little channel sitting elevated above the main frontal splay, and the frontal splay is 6 meters thick. So when you're thinking about seismic attributes or frequency content of seismic data sets, when you're trying to resolve these guys, when you're looking at logs, gamma ray logs, when you're looking for repeated parasequences, recognizable bodies of sand in deep water, it's 5 to 8 meters. Those are the building blocks in lobes, not 20, 30 meters at all. And underneath it, you can see it's got multiple tramline, fine-grained background stuff, but internally, there's no acoustic impedance contrast. It's completely massive, clean sand. And there are many analogies that you can make. You can look at eastern Tanzania, neocarbonatite lavas, low viscosity, watery, run very fast for these types of lavas. Also have that little lip. I'm reluctant to call it a leve. It's a leve, I know it's a raised area, but for most of us, leve means something that degrades due to spilling over on the sides of something. So I've been calling them different things, including leve, but let's think up a word some other day. Here we've got lips on the side, and they're due to freezing of the flow. That's what causes the axial shape. Here's Neil Kenyon next to some mud volcanoes, not from Trinidad, they're all in Italy. And there's a mud flow, as maybe some of you put power over there yesterday with Phil, where you see flows like this. And again, we have that tram line freezing on the edge of flows. The same type of thing we see on top of sandy flows. Very similar flow rheology. Mud can flow in a very similar way to sand that's moving in a lamellar pattern. And there are lots of other things like mine tail wasting and sand flows on dunes which have the same type of shape. One other diagnostic type of feature we see in distal deep water settings, far away on the edge of the system, are things called, we used to call them sandwich beds when I started working on turbidites in the late 1980s. And this type of sandwich bed was a turbidite. It was much thicker, about 1.5 meters, this one from southeast Turkey, in the Mycene-Adana Foreland Basin, where I do most of my work these days. and it was enveloped in very thin distal turbidites. Turbidites which have lost their energy, with no ripples or anything, just Bama T, D, and TE. So this was out of sequence. It was much thicker than the beds above and below it. But there are many of these types of beds. They're graded, they've got sharp bases. They often have a graded top, a normally graded top. That might be TA and then this grades at the top. But in the middle, they often have a dirty, scaly texture and outcrop. And these are what they call these linked debrites or cogenetic debrites. They're very, very common in deep water systems, but not that common. Where do you find them? On the fringes of some of these layered systems. They can be found at the edges, really the frozen edges of some of these distal systems. They're not found in proximal systems. They're rarely found in channels. They form by a range of mechanisms. Think back to everything you were ever told about turbidity currents, how a turbidity current starts. For example, you think of a slide, becomes a slump, becomes a debris flow like you see here in the upper diagram, and eventually mixes with more and more water, ambient fluid, seawater, and becomes more turbulent. So having a turbidity current spalling off an initial slump to debris flow is common. That's in our psyche. It's part of what we understand of deep water clastic sedimentology. However, we see lots of other beds that are formed in a different way. We see, for example, evidence for transformation of turbidity currents. So they're all going left to right on all these cartoons. This is mainly Peter Houghton's work from UCD, Belfast. There we go, turbulent turbidity current moving down slope. It's moving along the slope without any gradient change. And at some stage it just entrains some clay. So by gravity transformation, the lower part of the flow might trigger a debris flow. So a turbidity current, which would normally produce a normal graded bed, suddenly has this linked, allied, slurried debris flow running along with it. And these things can go a long way, and turbidity currents can stretch as they go. And as they stretch, the debris flow gets caught behind, the turbidity current deposits first, which you see here, and then the debris flow catches up with it. And the rest of the turbidity current comes out of suspension. So as a consequence, because you're relying on stretching of flows, these things are what you'd expect to find in very distal areas. So that, in 4 slides, is a very, very quick summary showing you where these things are located, that they're often associated with frontal splays. Here's an example, subsurface from the Kutai Basin in eastern Indonesian Borneo. So we're looking at areas outboard of the Mahakham Delta system, which is a tidal river-dominant mixed delta system. And there are a number of fields offshore related to the distal part of the Mahakham Delta, which are producing gas at the moment. The Gendalo field and other related fields are being produced by Chevron, for example, and our Sallows group did a lot of work on Gendalo and analogous near the seafloor features related to this. And they found lots of turbidites, but they found a splay-dominated system. So this is the composite Pleistocene analogue that they use just up here to the north. It's just 250,000 years old, this guy. And overall, it's got a vertical thickness of up to 90 meters. It's a big composite body, 20 kilometers in each direction, being fed by a canyon. And that could be mapped on most of our seismic data sets as a body that will be a resource fairway, that will be primarily sand associated. So let's have a quick look at it. On seismic, on the shallow seismic, they managed to manually map, which is not done often enough these days, individual geobodies. And these geobodies, within the larger fan, you call lobes. So these lobes are on a smaller scale. These are getting closer to the things I've been describing for you. All of these have different numbers. They're all laterally stepping around each other. They're separated from each other, more importantly, by thin clay drapes. And on seismic, you can have a look at these things here. The yellow is the top of the interval that we're looking at, more or less. The green is the lower part of most of what we're looking at. So these are the lobes on seismic. Above them we have levee channels with large aggregational channelized systems, and above that we've got fine grains as the system dies. But the timing of all of these lobes is during falling sea level. Underneath it, the eagle-eye view we'll see there's lots of chaotic stuff. So we get slumps and debris flows first. This happens as sea level starts to fall, as methane starts to escape from the upper slope and things start to collapse. Then we get these lobes, then we get levee channels, and then we get a shale drain. That's a classic cycle that we see in deep water. So this is what the bodies look like, lobes B, E, F, G. Let me give you 3 quick examples to show you what the different shapes look like. Here is lobe K. Lobe K, I'm sure you won't remember it, but it's up here. I struggle to remember sometimes. But there's K up here. Quite a radial feature. It's got a shape that looks broadly symmetrical. It's fed from over this direction, and it's actually made up of not one single body, but multiple bodies, of multiple splays. And the splays are all touching each other. This is a very nicely communicating body of sand, 5 kilometers long or so. But even so, we still have some areas where there is not communication. So that's one type of frontal splay from seismic. The second type is lobe N, much more of a frond shape, much more elongated, and much more like the Mississippi Gulf or the Cadiz types of lobes. And these types of features don't touch each other, and also they're made up of smaller scale individual splays. So fan, lobe, splay. That's their terminology, which is not so bad, really. And even skinnier ones, we've got these really delicate spindly features which form very frondescent edges. They're relatively thin, and those will be the other end. So you've got radial, coalesced or clustered frontal splays, which are sandier and well communicated. And on the other end, you've got more elongate bodies like you see here. So applying this back to the shallower parts of the slightly deeper parts, reservoir intervals, offshore Kalimantan, and looking at the gamma ray logs, and this is what we see. And even from a distance, you can see that most of these are bite-shaped thicknesses of reservoir body. This one here is a similar thickness to this one here, and that one here is similar thickness. And all of these things are 20, 30, 40 meters thick. So they're still too thick to be individual frontal splays. The cores show a whole range of grain sizes. Most of them tend to be more Balma-like, more TATBTC, more ripples, more interbedded shales and things like that. The dark colours you see here is plant material. And as everyone knows, most turbidite sequences are full of transported carbonaceous material. Everywhere you go, you see transported plant material, particularly at lower latitudes. All of the circum-Mediterranean basins are full of plant material in turbidites. And here off eastern Kalimantan in the Pleistocene, from monsoonal floods, the rivers in the Mahakham Delta are carrying huge volumes of transported plant material in the turbidity currents. You can pull logs out of the seafloor inside these turbidites. And these types of plant material, the carbonaceous plant material, are the only source rock here. There is no preserved type 2 organic marine oil-prone shale rocks here in eastern Kalimantan. It's all being moved away by very strong bottom currents. It doesn't accumulate. So here, the source rock are the turbidites, type 3 gas-prone turbidites. Who would have thought it? The turbidites produce the gas. And that's quite an unusual one in many places, that there's enough to be source rock, but it's a typical thing that you drop gravity cores anywhere in deep water in turbidites and you'll get plant material. So the bodies that we see here have a range of geometries. There's the splay-dominated bodies. This is from the reservoir modeling, so if you're working with IRAP, RMS, or Petrel, or whatever you want, and you're trying to define geobodies, instead of having a big radial fan with equal likelihood of getting thick sands, you can now have isolated bodies, or even more isolated bodies, or even stringy, skinny channels. And now we're getting somewhere, because now we have something that really looks like what we see on the seafloor. We're obliged to bring back this, because our reservoirs will feel the connectivity, believe me, as we go down the roads. We'll begin to see where these things are not peeling out. This table from the art style at work shows the lobes from that one fan. It shows the relative, I don't want to show you the thickness. It shows the thicknesses of each of these lobes as being anywhere between, what's the lobes, 26 and 46 meters. So these are the composite bodies. They're not the individual bodies inside the individual lobes. Let's go away from Kalimantan for just a few moments I am trying to watch the time and I do talk too much. The Amazon fan. 2 ocean drilling program legs looking at the leve channels and the mass transport complexes. Very well known papers, etc., etc. Recently, the missing piece of the jigsaw puzzle, they went back and looked at what was beyond the leve channel complexes, and yes, of course, they found lobes, but they didn't use what I prefer. They used EM12, which is a backscatter type of tool. They didn't use deep-toed side scans. So EM12 is a hull-mounted, very nice, quick way of mapping the seafloor, but just not quite as nice as some of the images that I showed you, purely because it's slower. Right? So deep-toed side scan sonar would break out these purples and blues and yellows, I would suspect, into much smaller bodies. But what was fantastic about this, as a starter for 10, was that they distinguished 2 different end members of lobes on the Amazon fan. One was number 2, radial, and one was elongated. The 2 end members that were already with. This is quite new, really, in terms of reservoir application. If we go back to Kalimantan for a moment, back to where we were with lobes A, B, C, D, E, etc., etc., and then we look at the mappable splays within the main lobes, in the frontal splays, then we see thicknesses of 10, 8, 6, 5, 10, 11, 12. And now we're right back into the ballpark. These are the bodies we can core on the seafloor, and now we can go back and look at outcrops to see exactly the same thing. So the building blocks of deep water sheet systems, the reservoir bodies, are not 40-meter thick bodies, they're 8-meter or 5-meter thick bodies. And the more you look, the more you find. I've worked in PetroChina for the last several years. This is work we did in Equatorial Guinea. Just old school stuff, getting on your workstation, finding an image you like, printing it out, and getting a bit of tracing paper and a pen, and starting to draw around the amplitudes. Just making very simple cartoons. And these were what we found in certain parts of the subsurface. These long, tongue-shaped bodies, which were 2.5 kilometers long, fed by these double-track skinny channels, forming these isolated blobs. Nice little bodies, stratigraphically trapped, upping your strat trap potential in deep water, not requiring any structure. That's the real data, if you didn't believe in my cartoon. Okay, they're all over the place, tadpoles. Below those, in this Equatorial Guinea example, and I can take you to the South China Sea, to any parts of the Bay of Bengal, to all deep water systems in fine-grained parts of the Miocene of West Africa, anywhere around here, and also in the other parts of the Caribbean. And we have the other type of body, which are the radial frontal splays. So these are the 2 end members. These are the higher net to gross, better connected, but there is still a similar thickness to the skinny ones. Here's one from Myanmar. This is one of the few producing gas fields. These are all biogenic gas plays in the northeast parts of the Bay of Bengal. This is produced by Daewoo. This is at shell-filled water depths, but in a deep water section. And there's one of these few fan lobes. And the reason I like to show this, this diagram is because if you look at it as a snapshot, it looks like you've got a feeder channel coming down onto a lobe. Then you look at it again, and you see the feeder channel, supposedly, goes off in this direction and continues around the lobe. In fact, there's another channel which seems to feed it with a mud fill, and that also goes over the lobe. There's another channel here that goes somewhere else. But there's a mindset which says if there's a channel and a lobe, they must be connected. And in fact, this is stratigraphically trapped up dip into the enveloping slope shales. So they're often isolated bodies, not connected. So let me roll this to a screeching, slow death of a talk, and let's take you through some models and some ideas, maybe just to throw them out, and maybe you can give me some of your thoughts on it. The timing and evolution of frontal splays. This is work I was doing in ultra deep water Magdalena system offshore Colombia, and we've been mapping these things for long distances. And hey presto, we have uncanyonized in the upper part, gullies feeding down the slope into the leve channel complexes, and way down the end again we have mappable thin lobey bodies. But everything in between is really very, very reservoir sparse. It's something that would scare you away from a system like this, and yet way down here we've got individual bodies 3, 4, 5 kilometers across, 5, 8, 10 meters thick individually, forming either clustered or individual elongate frontal splays. An example from the distal part of the Congo fan or the Zaire fan. Again, this is mapped by EM12, but it shows things that look like a bunch of grapes. So the bodies 1, 2, 3, 4 are bodies which are more on the 20 kilometer scale, but as I've shown you, when we have looked more closely, we've seen all of these things are always composite bodies. The youngest one is body number 5, and as you pointed out to me today, that is exactly the sort of individual body that we're looking for. When you think about the timing of these lobes, each of these lobes is about 300 kilometers from the base slope, offshore western Congo and Angola. So we're a long, long way out in the basin floor. So these sandy bodies have come many hundreds of kilometers. The timing of these flows you can work out. So if you go back up to the canyon that feeds these systems and count all the levee channels that feed on the fan and cut it down and down and down, these work out at about 650 years only between each lobe. So your frontal splays, you're almost back to Tuesday morning and Wednesday afternoon. They are individual flow deposits. They're every few years during a lowered sea level. They're very voluminous and they're coming from, usually driven by sustained hyperpictal flows from the rivers. Back to Kalimantan again. I'm sorry for giving you geographical whiplash, but I'm trying to give you technical continuity just to show you that things look very, very similar. So over on the left-hand side, we have a stage from the shelf edge going towards the east, downslope. And the colours here don't really show you, they're not proxies for amplitudes for sand, just showing you shapes. The edge here is the start of the formation of shelf edge deltas. So sand is starting to be sequestered on the outer part of the shelf just as sea level is falling. However, not yet, because sand is still bypassing the shelf edge from inside valleys into canyons and gullies, but right down the slope and depositing as these sand-rich, clustered frontal splays. And as you continue with the sea level to the start of the low stand, so falling stage to low stand, where the sea level is static and low, the sand is now sequestered in the delta lobes, most of it. So the only sediment coming out here is going to be river floods, mostly fine-grained material. And instantly, you get a change from linear channels with clustered frontal splays to skinny, wobbly channels with more elongate frontal splays. And that's the architecture always, going from falling stage to low stand, then transgression, you shut it all off again. So sequence stratigraphy appears to have potentially a lot of linkage to the shapes of the reservoirs that we see in these systems. So why, when and why do we get frontal splay? Why does a channel turn into a splay? There are various matrices that can lead us along. This is just a discussion matrix. So on the y-axis we have the increased degree of levee breaching. So channel axis, channel margin, levee, and overbank area. So if you manage to cut out and deeply down into the levee, you're more likely, wouldn't you think, to get some sort of switching of the channel. So with deep breaching up here, we get these lobes and splays and things. With shallow breaching, we only get crevasse splays. In other words, those holes in the levee can eventually heal up and the channel will chug along its merry way. And if you've got very little bit of breaching, we only get thin beds spilling over into the channels. So, number one is that we must have high levees to stop the formation of lobes. So as you come down the levee channels, outboard onto the basin floor, the lower levee heights mean it's more likely to get lobe forms and crevasse splays forming at the end. Not unlike river systems, right? Crevasse splays are much more common on the end of floodplains than they are higher up on the fluvial reaches. Deltas, the same thing. Also, on the x-axis, we have gradients. Now, adjacent gradients, if you've got a high gradient adjacent to a channel, it means the channel itself doesn't like being so elevated. So it's more likely to try to produce a more steady gradient profile. It wants to go down. That's all that x-axis is saying here. So again, that will preferentially, the degree of gradient increase next to a channel and the height of the levee. These are all these parameters. One set of ideas. The second set of ideas are probably more user-friendly, I suppose, because they bring together 2 or 3 parameters that are very closely allied. If you use the inset diagram here, you can see we've got a levate channel becomes a frontal splay. So that's all that says. At some stage, a levate channel will become a frontal splay. So that's the transition point. And in this matrix, we use the degree of slope curvature, so a high degree of curvature or a low degree of curvature. And on the bottom, we've got the caliber of the sediment now. So we've got a third new parameter, apart from gradient-related stuff, or degree of gradient change, or height of levee. We're now chucking in whether it's a fine-grained system or a sandy system. So you can probably put these two diagrams together into but I haven't worked out how to do that yet. So for example, high curvature like this. A high degree of curvature and a low, let's go this way, and a high amount of sand. So high slope change, lots of sand, you're going to deposit frontal splays more quickly. If you've got a low degree of curvature, so that's where that arrow is here. You see the transition? If you go down here, a low degree of curvature, so a gradually decreasing concave upward slope profile, and a low amount of sand, so lots of clay. Lots of clay in the flow means it's more efficient, so it goes further. So conversely here. So I was asked a question like this today, and that really neatly shows you what happens. Which means that on a big fan, sometimes way down here you'll have a splay, and the next splay might form way up here, the next one might form way down there. It's all to do with local conditions and the type of flow that's coming down at that particular time. And this is shown here. This is a Vencola's diagram from the Zaire fan, but most of it, I guess, would come initially from his ideas from the Indus fan. He shows a canyon, it's a concertina, the whole thing here. And L is lobe form, and H is harp, or crevasse splay, let's say, when a channel breaches. And here you've got a whole series of avulsion node points. So if you imagine you're standing out here on top of a sandy lobe or a frontal splay, and every few years you get completely doused with sticky laminar flow sand. If you're over here, nothing's happening for considerable periods of time. So in other words, not every single part of the fan is active at the same time. In fact, the only way to think about turbidite systems at any one time, I think, is that they're individual linear systems going duk, 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 until they avulse and go duk, 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 like this. And that's how the deeper centers are shifting in deep water. It explains an awful lot about the connectivity issues. H, being harp, will represent what happens when you break out of a levee and spill out sand onto the adjacent sea floor. And the channel will then have will reroute, has a new direction over the top of that harp, forming a shunting of the frontal splays until the whole gradient profile lowers and it decides to avulse again. Very clever diagram. And this concept of a channel breaching to form initially a crevasse splay or a harp and then forming a lobe, I've put together in this very well-drawn diagram that I didn't make last night. I just haven't drawn it up yet. But there's a levate channel. A flow comes along at a certain time that's out of equilibrium with the channel platform. It's high energy and it just breaks through a levee at a certain point. And initially, you'll have a crevasse splay. As you completely avulse the channel, it becomes a frontal splay. And as reservoir prospects, it's often, understandably, impossible to distinguish between a splay body, initially a crevasse splay, and the frontal splays that form in front of it. That's just another point. So to summarize with a few word slides, some of the things that I've been throwing out and pulling from different directions. The timing of frontal splays. We've seen why they form. They form at the most distal parts of systems. If they're very sandy, they'll form more proximally. If the system is more clay-rich, you're more likely to have a levate channel, so they'll go more distally. So sequence stratigraphic models of the past with the basin floor fan shifting to a slope fan, I'm departing somewhat from that because initial sandy fans must change into outstepping slope fans, more elongated splays. So when do they happen? Turbidity currents, we know, cut into older frontal splays. So we know that these sandy frontal splays are initially associated with higher density, slurry types of turbidity currents, laminar flows, the sorts of flows that can carry, if it wants to, pebbles or coarser grained sand. But most of the examples I've shown you just happen to be finer grained sand. They accumulate during the late part of the falling stage systems tract. They fall as sea level is dropping, as the insides valleys are cutting down and cannibalizing sand from high stand deltas and the shore and the shelf area. They're pumping sand out, and these sands are very concentrated flows, gravity flows, and they're what dominates on these frontal splays. And then later we get these more elongated frontal splays. As you come down to the low stand of sea level, as sea level is static, and you're keeping most of your sand in low stand deltas, then all you're getting out here will be more sustained, fine-grained river flood-driven turbidity currents predominantly. And these will give you levee channels and elongated frontal splays. It could be rubbish, but it's certainly something you see everywhere, so what can I say? It's definitely a pattern that continues, that you can see again and again and again. And what I want is for people to test these ideas about splay and lobe architecture. So during the falling stage, incised valleys on the shelf, canyons also cut down, and gullies cut down on the shelf break and slope, cut downwards, and we also get slumping at this time. So immediately before the frontal splays, we start to get large-scale destabilization of the upper slope. That's where you get the mass transport complexes and slumps and debris flows, etc. here. Then in the late falling stage, those incised valleys now are tipping into the canyon heads, passing down slope into the frontal splays I've been talking about. That's the main time of deposition of sand in deep water during the falling stage systems tract, with all the complications of ponding and sequestration of sand as you go down irregular. We know about that, but let's start with this, and then we can start to peel back all the complexities of sand ponding on slopes. This is where the sand gets in. At the low stand, we now have fluvial channels. The incised valleys start to fill with fluvial sediment. The deltas start to become more progradational as a low stand wedge. So most of the sediment is trapped at the shelf edge and on the newly exposed floodplains of the shelf. So low density turbidity currents are coming out, not high density. So we get the deposition of slope fan, or you can cross that out if you want to, put levee channels and elongate frontal splays. That's the main thing. So this is a diagram I put together to try and just get you thinking, just a testable type of platform model for the shelf edge, down through slope canyons and slope confined canyon systems, confined channel systems with levees eventually. I've put in here slumps and mass transport complexes on the slope. Most of the turbidity currents, of course, will be funneled down the canyon. And at different times, I've tried to superimpose different scenarios in the same place. So first of all, this scenario. How likely is this scenario? Well, how often do we see a really sandy fan? Well, the answer is we don't know, because I've only shown you the 6 examples that I know of 8 cruises that have ever sampled them on the modern seafloor. How common are these? I'm not so sure. And I wonder whether, particularly, I know it's not a question of high angle, high gradient, narrow shelf, coarse grained systems, because you see frontal splays as superfan lobes were defined from the Californian borderlands, these so-called coarse grained, high gradient proximal systems. So I wonder whether we ever see these, really. I wonder whether we aren't always looking at blobs that look like this, of clustered frontal splays at the sandiest time in deep water, with the exceptions of what a trough might do if it confines them. All those things, of course. But let's just imagine it's a bit flat. This will be 5 or 6 kilometers across maybe. And superimposed on that during the finer time, during a low stand, these leveed, squiggly things come right out to the edge of the system, like we see in the Mississippi, Magdalena, Orinoco, Nile, Bengal, Indus, you name it, they're all out there. Irrawaddy, Mekong, I suppose, as well. So those are the frontal splays, different types, cluster frontal splays and more elongated frontal splays. And to end on a very dramatic diagram, a photograph from a class, just to show you the sequential ideas behind this. Early falling stage systems tract, shelf edge, incised valley incision, slump scars, and lots of slumping on the slope. And slumping, by the way, large-scale excavation by slumping on the upper slope is how canyons initiate originally. Canyons eventually form by retrogressive failure on the slope. And they form conduits and fairways eventually, which will tap back onto the shelf during the late falling stage systems tract. I never used sequence stratigraphy for 16 years. I never mentioned sea level on field courses. And suddenly I became poisoned by what was happening on the upper slope. Because finally we found surfaces that we could correlate. And it wasn't the base of incised valleys necessarily, it was the base of the slumps. That's the sequence boundary. That's the Exxon style sequence boundary. It's only after that we start to see the sands coming in. We start to see the clustered frontal splays. We start to see bypass inside the canyons, residual gravel-like conglomerates, what I call smoking guns. And on top of that, superimposed red on black, green on red. Same system here. Now we've got low stand deltas prograding out, fed by the fluvial fitting of incised valleys, downlapping onto a continental slope, occasional high density, or excuse me, low density underflows when you exceed a particular density threshold from suspended load from the rivers. That will drive these hyperpictal flows directly by some river floods, and these are sustained. So you have skinny channels, you even have point bars inside levees and things, as these snakes making love come all the way down the canyons and feed out onto these elongate frontal splays. So back to the initial questions. What do lobes look like? Well, I hope I've shown you what lobes look like. They're composite bodies. They're made up of bodies which touch each other, which I'm trying to call clustered frontal splays. I don't mind what term people use, as long as we're talking about the same thing. There aren't very many examples of them sampled, but there are, if you look, more and more. Or we have these elongate frontal splays, which are a very different type of end member body with poor communication. They often have a radial halo around them of dendrites, of these hybrid beds particularly, and they're very diagnostic. What are the questions that I ask? How do frontal splays fit into sequence stratigraphy? There's another question. How are we looking at the right things? Well, I think we are now. So I'm hoping that bit by bit we really try and combine different data sets, that we iterate between beautiful subsurface data sets and rubbish subsurface data sets with seafloor analog data that you think can be applicable, and with outcrop data, core and wireline. We need all of these in our box of tools to shake it around to get an understanding of what frontal splays are. Okay, thank you very much.
Thank you very much. I'm sure Professor Incredible will take a few questions. If you could give your name and affiliation before you ask. Paisley, please.
Good evening, everyone. Good evening, Professor. I really enjoyed that talk. He's Vincent, currently a second ecologist with GSTT. You gave us so much that questions came and they disappeared. And I'm going to try to, there's one that I sort of stuck. Where are we now in terms of understanding that termination at the frontal end of those splays? So you described a very dramatic end from very, very sandy cores into pretty much miles and months. I know there's a lot of, there used to be a lot of debate in the literature on the process. Where are we now in understanding the processes that really governs that transition, a very sharp transition, as opposed to sort of the models that predict a more distal transition into the deep water?
Most of the, great, thank you for your question. Most of the transitions that we see, that we've been modeling, are in the North Sea, for example, are lateral pinch-outs of sand, layered sand sheets onto confining slopes. And a lot of the effort we've been using on that particular theme is of a non-lobate type of body pinch-out. So, but they're of interest to us because we're working in those types of topographically confined sheet systems without the bigger lobes. So the types of application where we are now would be layered sands, also in the Gulf of Mexico salt withdrawal basins. Layered sands tend to arithmetically decline the reservoir quality towards pinch-outs. So when you look at infill wells or sidetracking things, get the last stuff out, versus more lower, higher gradient confinement. So thin beds on low gradients, thicker beds on high gradients. Thicker beds tend to pinch out very, very rapidly. So there's more of a, not logarithmic, but a really, really quick pinch out with reservoir quality write-up. So a lot of our effort over my recent memory of working in the North Sea would be that type of thing. Globally, if you're thinking about research groups and various things that are going on, people are looking, of course, at these things. A lot of efforts being made on these debris, these linked debris, these co-kinetic turbulence and things. But I really feel, until we have enough collation of examples from the subsurface, like I've shown the Arsala group from Kalimantan, for example, with modern data, we're not there. We're not anywhere near there yet. I really feel that. I think channels are so much. I've always been, my PhD was always channels. And even I remember there was that moment in a meeting in Al Madinah in 1998, where we had all these people from the different oil companies, research groups, talking about the proliferation of reservoir styles. We spent, John Kendrick said that of Shell's deepwater fields in the Gulf of Mexico, 60% of all their producing fields were from amalgamated sheet sands. 25% were from layered sheet sands, and 15% are from levic channels. And we spent the next 3 days talking about levic channels. So there's a, I don't know, it's been left sitting there for a long time, I think. Where I think we are, and that might be different to your question, but where I think we are is that a lot of potential is being ignored because of the upside of having sand out there in the first place. We've been producing from amalgamated sheet sands since Bullwinkle and Auger and Mars in the early 1990s. And that from when Auger came on stream in 1990 in the western part of the Gulf of Mexico, they'd never produced from amalgamated sheet sands before. Now 1990 doesn't sound like a long time ago to me, but we have a lot of experience from those types of very confined sheets. What we don't have a lot of experience of is what I've been talking about, the more distal development. Or even late field life in some of the lobes that we have been producing from. Think of any high net to gross field you could mention, let it go for a few years, fine, and then the geologists get scared off, the engineers take over, and then the problems start, and then they realize how compartmentalized it is, as always. So I guess we need some more time for some of the examples of Kalimantan. So in comparison to channels, low, I would think.
Any other questions?
Yeah.
So could you please say who your
Yeah,
name and affiliation?
range resources. So one can describe these as like toe sands. Have you ever seen these on seismic, where you can actually see it on a line, let's say, going parallel to the flow? Can you actually, have you ever seen examples of them on seismic, given the dimensions that you mentioned?
Yeah. Of the ends of the splays?
Yeah, where they abruptly stop, where you can actually see maybe some anomalous reflector type array that would previously not be properly interpreted, but that you can interpret as this.
Yes, the example, I gave you some examples from Equatorial Guinea,
Yeah.
which show these ones on the right-hand side, the elongated frontal splays on the left. So there's quite a lot of them, and they have very rapid terminations, almost all of them. I'm working on stuff offshore Ghana for the last few years, and I'm just amazed how many of these things we're looking at. The sand-prone ones, like you see in the red, the cluster ones, and the elongated. And we see them in either in dip section on reflection profiles. You can see them pinching out quite rapidly. But of course, mostly what you see in reflection seismic profiles will be the composite bodies, rather than the individual splays, like the amplitude maps I showed from Kalimantan. So you have to sort of map the geobodies themselves. So you have to tease them out. And yes, of course, I mean, I've shown you what 60 Hertz seismic data, half a kilometer or something. So the frequency content is quite high. And most of the industry seismic group we would be looking at that depth would be 25 Hertz, I suppose. So they're normally just below the seismic resolution. And most people's maps, dashed lines around their fans, are because they can't see them. And they're not expecting them. And even really sandy stuff in the North Sea on the Atlantic margin It's amazing how sheet-like some of these fans look like, and they start producing from them, and they're compartmentalized by the drapes that separate the different things. So you don't always see them, of course, but that's part of the problem. They're there, we just don't.
So you're saying if you think they're there, maybe then you can deal with them. Yeah.
And you can start looking at well trajectories that are more reasonable for the types of bodies that you expect. Because you know their orientation, you know their connectivity. So there's that issue for sure. You don't always see them. You see the composite bodies usually. And of course, I'm only going to show you the fantastic examples. There may be some here, who knows? Or who's not saying.
Great. Well, I'm going to stop the questions. I'm sure Professor Cronin will be happy to talk to you during the meal or later on if you have a question you can think of later on. On behalf of GSTT, I'd like to thank Professor Cronin for an excellent talk. I certainly learned a lot from it. I thought it was very clear, very well illustrated, covered some aspects of geology that I certainly haven't been familiar with. So please join me in a round of applause. Yep.